review, well, silicon band gap is 1.1 eV or 1.1 electron volts, and germanium stands at 0.67. Well, I'm going to discuss about what we have to deal with that. Well, this is just a demonstration of what exactly happens when a photon or a quanta of light hits the electron or hits the valence dot. Now, once it hits that, the electron from valence band, it enters or it excites or jumps on the conduction band, leaving a hole in the valence band. So the blue dotted ones are the holes, are the electrons, and the black are the holes. And they just leave the holes down in the valence, and then when they jump up to the conduction, that's how the conduction process goes on. And then we try to, this flow we try to generate electricity out of it. Okay, now what exactly are semiconductor elements? We do have two types of semiconductors, N types and P types. N types are those which are doped with, okay, let me get into doping. Doping is nothing but it's trying to give a negative impurity, negative input in order to get a positive output. That's what we do up here. We try to impure it with some kind of other group elements like phosphorus for N type, so that we get a desired characteristics. And then also for P type, also you try to dope it with boron in order to get feasible characteristics. So what exactly are these semiconductors? At a glance, we have these intrinsic semiconductors, that's the purest form of semiconductors. N type and P type are as usual doped with phosphorus and boron respectively. And this is nothing but how the conduction goes on from when electron jumps from lower level to higher level from valence band to conduction band. This is just for demonstration. Okay, this is the N type. N type has electrons in neutrality and P type has holes in neutrality. All that we try to do is that these have built-in potential in it. These have built-in potentials. In fact, PN junctions, PIN junctions, Schottky barriers, they have built-in potentials in it. So we try to utilize that electric field. We try to utilize that electric field. Now, the electron from these holes from here, electrons from here, they try to diffuse to that, and the holes up here, they try to diffuse to that. So we try to generate some kind of electric field. What exactly does it happen? Now, once my light falls on that, on the film, it tries to break the silicon bonds. It tries to excite those electrons, and then it separates those the holes and electrons. There you go. That's what it is. So, as you know, it will be opposite direction. The electron flow in one direction, the current flow will be in the other direction. At a glance, let me try to encapsulate everything. Solar cell is nothing but a sandwich of N type and P type just placed together. And once the light falls into that, the photon, the yellow dot are nothing but photons. They try to go through these P type, and then they give that energy. Photons are nothing but energy. It's nothing but, okay, if I try to kick the rod, I try to give my energy to that, but I'm not destroying it. Here's the fact that I'm not trying to destroy the energy. I'm trying to change it from one form to another. And then you're giving energy to the electron, and then this electron use this energy to jump across the barrier into the upper layer, and then we're trying to lift off from there. So it's a whole concept of semiconductors. It's just a fundamental, but we are trying to hide it since almost 20 years. Alright, that's what film looks like. We try to have this back metal contacts. Try to put the metal contacts so that we need to drag, capture the electricity of the electrons. And then we have the N type and the P types, and on top of that we have the fingers or the metal fingers or aluminum rods. In fact, recently they came up with the nanometer rods. They're really tiny, but in order to capture all the light, this surface should be able to capture all the sunlight. That's the main efficiency that's where the solar cell lies. And we kind of have some kind of advantage with possible protect it from the weathering and the other factors.
Did they put any kind of coating on it?
Yeah.
That's coating? Yeah, but how about the coating? Like for example, if you take the automobile, that automobile always have more heat. They decide to put sunlight to affect the sunlight on the surface. Do they put some coating?
Yeah, they do. In fact, that's the main motto that they have to capture all that power. That's the reason the efficiency say that recently the very advanced efficiency was like 25 or 26%. If you get almost like 1000 watts of power, it's just within 26 or 260 watts of power. So, but they're trying to increase that absorption factors. This is just for information about the visible spectrum from 400 to 700 nanometers, and that ranges from 1.7 to 3.1 EVs on the electron volts. So these are one of the criteria what we might be looking for solar cell designing. V as well as 1.8 EV. Yeah, exactly. Because sunlight is almost like 1.8 or 1.9 EV, so that should be enough to pick the silicon bonds. Silicon is like 1.1 and has enough energy to pick the silicon. Similarly, as narrow as possible. More sunlight. So here are some of the requirements what one might be looking as part of the semiconductor region. Bandgap 1.1 to 1.7 EV. Yeah, that's the reason most of them are depending on silicon and not the other ones. But they came up with the new one, gallium arsenide, some other CFGS, telluride. They're still using it because they are flying between that bands. Direct band gaps, yeah, we do have a direct band gap structure and indirect band gap structure. Direct band gaps, yeah, we can capture all those photons right away. Otherwise, in indirect, we definitely can't do that. And consisting of regularly level non-toxic silicon, silica. These are reproducible deposition techniques yet, ME or ion deposition or the solution processing methods. The photovoltaic conversion efficiency, that's what we need. Long-term stability, yeah, we need to check out whether how far on the, we don't want to change the solar panels for every year, so we need to have some kind of stability, how far are they stable for any kind of weather conditions and any factors.
So let me ask a question. Which part of the spectrum for the sun are you targeting to get the greatest energy?
In fact, if you look at visible, it's almost like 46%, and most of them would be visible and infrared.
Visible and infrared.
Yeah. But because SUV is like 5%, so we're not worried about 5%. Alrighty, so what exactly are the photovoltaic technologies and how exactly are we going to categorize them? Alright, the first solar cell was discovered probably like in 1977, I guess, yeah. And that was based on silicon wafers. That was the first generation. And as Dr. Lau was saying about the amorphous and polycrystalline, they came up with another material like telluride. What Dr. Batra was saying about composition. These are nothing but man-made materials. Telluride. This would give us good efficiency. In fact, telluride is standing like 35% of efficiency. Also, copper indium gallium diselenide.
Telluride is expensive.
Yeah, it's expensive.
The white and the band gap is large too, right? For cadmium telluride, the band gap is wide too, right?
Yeah, band gap is wide, but in fact, it is more efficient. That's the reason we are just focusing on that. But it's expensive though. And there you go, third generation polymer solar cells and disulfide solar cells. That's what the physics department is working on, the polymer solar cells and disulfide. So let's have a glance at why exactly silicon. Silicon, as we all know, that okay, it's non-poisonous, and we don't want to have any kind of pollution out of it. Yeah, and in fact, it's an abundant element. That's the second issue. That was the major drawback why we have to drop from fuel cells. And it's an abundant element, and it's almost like 1/3 of the Earth's crust, and easily formed into monocrystalline forms, and we have endurance of 125 degrees C. And we can form almost like 99.98% of purity in silicon. So you can just imagine what kind of things. In fact, I have one kind of demo. They're trying to make a solar car on alternative for fuel cells. So just trying to make it solar so they can run it. I don't know when they're gonna. In fact, General Motors is working on it. General Motors is working on it. Alrighty. So what are the advantages? The high efficiency, 40 to 42%. We need that. Established technology. Yeah, it is silicon-based wafer cell, the leader in the solar cells. Apart from categorized as CFGS, but probably soon it's going to be overtaken by the polymer cells. And the major disadvantage is expensive production. We don't need that. We want to spend only $5 and get almost $10 a month. Low absorption coefficient, that's what we're discussing about. In fact, research is going on to augment these absorption coefficients and large amounts of highly purified stuff. If you could go through these, there's research going on at Stanford and other schools. They're trying to make this textured layer outer surface so that the light falling on this surface will be reflected back to this surface. So all that they're trying to do is they're trying to capture the photons. They don't want to lose any light. They want all the light, what it can grab, what it can collect, almost, or if you send 100 watts, then it needs to capture at least 60%. That's the major idea. In fact, they're trying to make out what kind of textures they can make out. Alrighty, so with all those disadvantages like less expensive and what else we have? Low absorption coefficients. Yeah. So let's see whether organic can overtake over that. Alright, if you look at the cost, it's like $95. Propagation cost, we just say low capital. In fact, $1 billion is highly costly for a small company. In fact, if it rolls roll, they came up with the new inkjet printers that you just have to put in the paper. This is nothing but the conducting polymer paper. You just have to put, and the ink tube is like the regular cartridge, HP cartridge what you get. You just put it and then you can print out the solar panels. These would be somewhat like the flexible solar cells. So I'm going to display it for you. This would be one of these solar cells. It is folded. As I said, this is nothing but also flexible. That can run under the regular bulb too. Alright, so why exactly organics? Well, we have a different blend of answers for that. In fact, all these days we're just thinking about inorganic, then raise the thought that, okay, why can't we go beyond inorganic? Why can't we go beyond inorganic, say that, how about organic? And that thought of Alan Eager was awarded the Nobel Prize in 2000 for his research on conducting polymers. There came into picture this polymer solar cells. Until unless that thought came out, we couldn't make up this dye sensitizer solar polymers.
When you need to fight figure again,
Right.
they accepted our invitation.
You're denied 4 times.
We have a problem here.
You want to make that a career? Go ahead again, Nikal.
I talked to him very time.
Alrighty, we have the air mass silicon, higher silicon for large mass air mass 1.5 spectrum. What exactly is an air mass or AM125 is it's nothing but the content of water vapor and temperature in the out of the above atmosphere. In order for solar radiation to pass, we need to have a clear AM45. That is most dependent on the inclination angle. Now, I have the solar panel up here. If my sun is up there, I have to face it this side. So what angle doesn't matter. So it should be at the angle of AM1.5 is like 48 degrees, and if it is 0, it's right away on top of 10. That's
Well, with your new material, would you be able to fully coat something so no matter what angle the sun is on?
Now it depends on the applications. In fact, the AM0 is used for space applications. So for all the commercial usage, we go for AM1.5, and AM0 is for all the space applications. They made a space satellite for solar, completely solar satellite. In fact, they also made a solar plane. They have no electricity for that. They have no battery for that. Let's be solar. So it all depends on the applications. As for AM1.5, 1.2, or 2, that differs.
If I wanted my home to be
1.5. 1.5, all the commercial applications. In fact, for all the other applications, we go for 1.5. For all the space, we go for zeros. Alrighty, it's relatively dramatically low production cost. Yeah, in fact, we just need probably a spin coater or a brush coater with that. Having the materials in the ambient conditions here. In fact, we don't have to have perfect conditions like a perfect clean room like we do it for silicons. We just have to. We can have. In fact, I can just fabricate it here. Organic electronics are light and flexible. As we know, this is brittle and this is strong. This is silicon one, and this is flexible solar cell. Lightweight. That's what we need. Less pollution and foldable. In fact, they came up with keyboards with solar, those flexible solar cells. You don't have to wire those. Low cost electronics, yeah. In fact, this gives an answer for all the disadvantages of silicon. We had an expensive in silicon, it suffices, and light and flexible, yeah, it does. Low cost electronics. That would be best answer for all the silicon. It would be best alternative for silicon electronics. And but what exactly would be? Also, they are biodegradable. As you know, organics are biodegradable. If you can look at sun chips, the bag of sun chips, they spent almost just $1 million plan for just the regular bag of chips. But the regular Doritos, the plastic chips, what they're made of, they're not biodegradable, and they spent almost $2.2 million per year. You can just imagine they're saving almost $1.2 million.